Well, look here. What do we have? This is another DC circuit problem applicable to an AP Physics C E&M course, probably assigned sometime after a lesson or two on Kirchhoff's laws. And I'm going to use those ideas to solve this problem. Although, if you saw the last video, you know that sometimes these problems can be a little atypical, and this is certainly one of those that has more of a surprising result than you might expect at first. If you look at the practice problems that are typical for this unit and even watch some of the videos you can find online, these problems tend to follow certain patterns. You find yourself writing loop equations and solving systems of equations, simultaneous equations with many unknowns. And that process is, after a while, becomes very rote. This problem is different, as was the last one that I did a video on, in that the solution ends up maybe kind of falling out a little sooner, a little more surprisingly than you might expect. And I really like questions like this, because if you're taking the AP Physics exam from the College Board in May, you'll find that they often do things along this line, as opposed to giving you a problem with 7 resistors and 7 different branches with 7 unknown currents and 2 or 3 batteries, which is really just a mathematical exercise. You're more likely to get something like this, where careful application and choice of which loops to look at and a deep conceptual understanding of the process will yield an answer much more quickly than just kind of plowing ahead and writing lots and lots of equations. So I'm going to attempt to tackle this one here now. I think, as I often do, it's probably a good idea to redraw this so that I have some space to work in rather than trying to work in this tiny diagram up here. So I'm going to do that right down here. Here's the battery there, and my first resistor, my switch. We'll put the ammeter in a moment. And just some random point labeled A, a second battery, which faces this way, a second resistor, like so, and then a voltmeter that is connected across both the resistor and the battery, so it's reading the combined potential difference across both of these elements. I don't love the way it's drawn in the diagram. It almost looks like it's another branch of the circuit, which of course it is, but having the huge resistance that voltmeters actually have, very little current ever traverses that path. So I'm actually going to draw it a bit differently. I'm going to put this here, put the voltmeter like this, and then just connect like so. And by doing that and using a different color, I hope I'm giving you the impression that, it's not really to be thought of as an alternative path for current flow. You don't have to consider this as another branch of the circuit, because that voltmeter has a huge resistance inside of it. All right, and I think right off the bat that's going to confuse a lot of people that are trying to do this problem when they see this path over here drawn as it is in the circuit. So let me go ahead and make that point right there. Okay, I'll put the ammeter in right there. Ammeters, by the way, have very little resistance. Voltmeters have a lot of resistance, so they don't draw much current, so very little current follows this path. You can assume no current, in fact, for the sake of the circuit solution. And ammeters are the opposite. They have very little current, so you can put them right in the flow of the charge, and they don't disturb things. They don't increase the resistance of that branch of the circuit. All right. And let's see what else. I've got the switch, which I have to draw. So that's the switch is initially open. And I call this point point A, and this point is just 2 arbitrary points, right? Point B. So I'm sure they're going to ask us a question about that later on. Here's the voltage, the resistance of that resistor. This one down here is 75. So this battery is 15 volts. That would bother me. And this battery over here is 25 volts, like so. And that's everything that I know, okay? And let's see what they're asking. Find the reading of the voltmeter with the switch open, and then tell me which point A or B is at the higher potential. Okay, let's go ahead and label some currents. as I always do in such a situation. Looks to me like I'm fairly confident that current flows this way in that direction. We'll call that I1. Now I have to consider if there's a junction here, do I need to define another current over here called I2, and perhaps a current in this branch here called I3? And the answer to that question is resoundingly no, because this switch is open, so there is no I3, and that means by continuity at this point right here, I1 just flows right across that junction. It's really not a junction. It just continues right on over here, and so really there is just I flowing around this entire circuit right there. So I can go ahead and get rid of these two currents, and I think just so that you don't forget this fact, we're just going to put I1 right back here. In fact, I'm just going to call it I. We don't need any subscript at all, right? One current. And now if you're watching this without a significant background in circuits, then you're probably wondering, well, wait, why doesn't something go, down here, at least as far as the end? Maybe do charges like kind of come down here and sort of sniff it out before they find out that there's a dead end? So maybe there was a little bit of current for a while and there's none. And I should probably make a video about those ideas and talk about what's going on really inside of circuits, as opposed to these kind of idealized constructs that we draw. And maybe someday I will. But for the time being, hopefully, that there is no current going down this branch, this dead end of this circuit. All right, and so we'll stop with that and just kind of go on to the problem at hand. So what can I do? Well, if I just sort of look at this outside loop all the way around, and I use the loop rule to analyze it, so we'll just kind of draw like so. I'm going to walk in this clockwise fashion around this loop using Kirchhoff's rule to figure out what's going on. I'll start right here, like so, and we'll just go around. So the sum of the voltage rises and drops must be equal to 0. I start off at the negative terminal of the battery and rise in voltage by 25 volts as I go across it. I then come here going in the direction of current from the higher potential to the lower potential side of the resistor. I then see a negative 100I, minus 100I IR drop, I times R across that resistor. I then keep going across here. From this point to this point, I see a plus 15 volt rise from the battery, and then I end up seeing, again going in the direction of the current I, a drop of 75 I, and that all has to sum to 0 when I'm back here. All right, that will allow me to calculate the current I, which is going to be useful for answering the first part of the question, which is to find the voltage reading V. And doing so, let's see, I wind up with 25 plus 30, that's 40 here. For some reason, doing math in real time while I'm making videos just stresses me out, and even the easiest calculations seem to get difficult. This is negative 175I. I think it's because I don't want to make a mistake in front of everybody. All right, so 40, yes, 30 and 40. Okay, 40 minus 175I equals 0, which gives me a current of 40 divided by 175, which I don't know in my head. It's 0.22, let's say 0.23, like so. 0.23 amps, and in a clockwise fashion. It did not come out negative. Why would it, right? Of course, that's the direction of the current in this circuit. Both batteries are pointing in such a way that it can't be anything but that. So conventional current flows clockwise around the circuit, and there you go. Now, to get an answer to the question at hand, what I want is just the potential difference between points A and B. So if I start at A and I just kind of walk along my circuit and I get to B, let me ask myself, what will I see just along that stretch of circuit? Certainly the sum of these voltage rises and drops does not have to be 0, because I'm not making a complete loop all the way around. I'm just starting at A and I'm going to B. So let's start at A and let's see what we find. So the first thing we find is a rise in voltage of 15 volts. So here, let me just write. This is from A to B. Okay, so we see first a rise of 15 volts, and then followed by a drop of IR. And I'm not making the claim that that's equal to anything in particular, right? It's the equals 0 part that I use here that's Kirchhoff's rule, and that's only true for a loop. So I don't know what this is equal to, but whatever it is, that's what I'm looking for. So this, of course, is 15 minus, because I just got done finding I. It's just 0.23 times R, which is 75, like so. And so running those numbers, I get 15 minus 0.23 times 75, which is negative 2.25. Find the reading of the voltmeter with the switch open. And I say that that is then volts as the potential difference between point A and point B. Okay. So I just want to point something out with regard to these numbers. So that is the answer, at least rounded. And what I did, I think, back here, when I rounded this to do decimal points, so I think I may have created a little bit of an inconsistency. I just want to show you what can sometimes happen with these problems. So I'm claiming that that's the answer, okay? And we'll get back to which is higher and which is lower in just a moment. But if I then look at a different way of coming to this conclusion, a different way of calculating the voltage from A to B, and that is, what if I were to start here and just sort of walk from this point, or really start at B, essentially, and walk all the way around and come over to A? What will I see as my potential difference? So this is now, instead of going from A to B, I'm saying from B to A. And that would look something like this. First, I would see the rise of 25 volts across the battery, and then I would see the drop, IR, across the resistor, which, using the current that I have over here of 0.23 amps, that would end up being 0.23 times 100, right? And that would then end up being the delta V, the voltage difference, from B to A. So running those numbers, I wind up with maybe something that's a little surprising. This only comes out to 2, comes up positive, in fact, positive 2 volts. And so at this point, there's a little discrepancy, because if I do the whole loop, I know that I have to come out with 0. Right? I started with that premise up here. And how is it then that I wind up with negative 2.25 when I go from A to B, but then only 2 when I go from B back to A? That seems completely incorrect, because theoretically these should be the exact same number, just one negative and one, positive. So something strikes me as being wrong. And really all it boils down to in this particular problem is the rounding of this number that I did right here. If in fact I had stuck with a couple more decimal places, and my friends who teach chemistry and significant figures can yell at me about this, but if in fact I had said 40 divided by 175 was not this here, not 0.23, but instead if I said it was 0.2286, let's say I kept that as my current, then that changes things a little bit. This here, if I replace that number in there and get rid of the 0.23, that changes this from negative 2.25 to 15 minus 0.2286 times 75 is negative 2.145 volts, which is arguably quite different than the here what I had, the 2.25. And doing the same thing over here, replacing this also with the 0.2286, right, would give me 25 minus 0.2286 times 100. And look at that, that actually comes out to, instead of 2 volts, it comes out to 2.14 volts. And so I'm just doing this to point out the fact that sometimes when you do these problems, you might, if you're checking yourself, you're checking your work later on to see if the voltage rises and drops add up and they make sense, you might actually be correct. but it could have been some rounding that you did earlier that leads to the results being what looks like different, significantly different. Okay, but so whatever you want the answer to be here is okay with me. But for now, for the time being, I'll just stick with that right there, negative 2.145. And again, we're looking from, it says which point is at a higher potential, A or B. The way this is a little bit, I think, nebulous which way the voltmeter is in fact hooked up. I don't know where the red and the black wires from this voltmeter are in here versus here. So I'm not exactly sure how we're using the voltmeter. We might be using it backwards incorrectly. So I'm not sure which of these answers I should report for the reading on that voltmeter. But I can tell you that A is at a higher potential than B, right? Because I'm losing voltage as I go from A to B. Overall, I'm losing voltage, right? And if you say, well, how does that work? We'll come back to the initial loop that I did over here, right? So if you just kind of look at it in stages, so take the 0.2286 and plug that in right there for I. And you'll realize, okay, you start off at 25 volts, and then let's subtract out. So let's go 25 minus 0.2286 times 100, right? And that leaves me with 2.14 volts positive, which is what I have here. So if I started at this point right here and started to walk around my circuit, at this point right here, I still have positive 2.14 volts. That is my voltage relative to this point here, which I'm assuming I'm calling ground, or 0 in this case. So I'm still in positive voltage land. And so I've got to get back to 0. So as I come from here to here, overall, this appears as a drop in voltage. I realize I gain 15 volts across the battery, but I end up losing more across the 75 ohm resistor than I gain across the battery. So all told, from here to here, I must end up seeing a drop of negative 2.145 volts to get me back to 0. So that means, in fact, that this is the higher potential spot right here. High potential, or higher potential. And this is the lower potential side right here. Okay? All right, now I close the switch, and as always, with every good problem like this, things change dramatically. The switch is now closed. Notice, though, there's no resistance anywhere in this branch of the circuit from here to here. All right, and I'm going to erase the work that I've done over there because I'm assuming that it's probably not pertinent anymore to what's going on. So let's get rid of this. All right, what do I do? The question is to find the reading on the ammeter this time. What is the reading inside in that middle branch of the circuit on that ammeter with the switch closed like so? I'm going to get rid of this loop as well because I might not use it. Okay. Great. Well, with the switch closed, the bad news is that now there's a second current in the circuit that I have to consider. So let me go back and start labeling these currents as I think I probably should. So this current I'll call I1. And this current over here, which is leaving this junction and flowing through this battery, and I will assume it's in this direction, I will call I2. And this current, which I'm going to sort of just arbitrarily choose as being down, I'll call I3, like that. Again, there's no resistance in between these 2 points with a perfect ammeter, but I still have some current traversing that section of wire right there. And of course, I know by the junction rule immediately that I can say that I1 equals I2 plus I3. Great. Now what? Now let's try to do some work with the loop rule to figure out what's going on with any of these currents. Let's see what we can do. So the first thing I'm going to do is make a loop like this around just that left-hand section of the circuit like that, and I'll start kind of traditionally here below the battery, and I'll just walk my way around like so, and I'm going to really gain a significant advantage from the fact that there's no resistor in this central branch of the circuit. So my loop will look like this. I'll start off with 25 volts, positive, and then I'll see a voltage drop of 100 I1. I've gotten through that resistor. I now turn here, I go through here. Again, no other resistor to worry about. So the no voltage drop here and no voltage drop again until I get back to the battery. So actually, I'm done. And that's equal to that right there. And I immediately can tell you that this is 0.25 or a quarter of an amp. 25 divided by 100. Great. All right, I found I1. I suppose I should write that in pink. 0.25 amps. Great. All right. I stress once again, before I go on to the next loop, how convenient it was that there was not a resistor in here. Had there been, then this equation would have wound up with another, it would have had another term in it. It would have been something like, just assuming that this is just called little r for resistance, it would, and you know it, but it's called little r for me. Then this would have been I3 times r equals 0, and that would immediately complicate things tremendously, because now I can't just solve for this value of I1. I can't just know it, and I'd have to go back and look at this equation, this loop here, and I'd wind up having to solve a system of equations to try to figure out what's going on. But, you know, guess I've been given a gift here in that I don't have to do that. And that's why I said at the beginning of the video, very often with these Kirchhoff law problems, you know, you tend to do problems for homework that have scenarios where, yeah, there would be a resistor there, and you'd wind up having to solve systems of equations to get the values you're looking for. But when you take the AP test, what you'll find often is that circuits tend to be more like this. They just kind of simplify it a little bit, so you spend a little less time with the math and a little more time diving into the conceptual issues at hand. Okay, so I'm done with that. Let's do another loop, because obviously I'm going to have to find out I2 to really know what I3 is all about. So let's do this loop that I'm drawing here in blue, like that. Let's start here, and we'll walk our way around. So that loop is, it looks like this. I'm going to say 15 minus 75 I2 as I go across this resistor in the direction of current flow, and then back around through here. Again, no resistor in this middle branch, so I'm done. That's it. No more voltage drops, and I have a 0 right there. Had I been given a resistor inside this middle branch, then I would have had to have a, you know, something with an I3 in here, and that would have been the same variable I had in this other equation. Then we could solve the system. But it's easier than that. I don't have to worry about that, and so I'm essentially done with this. So then I can just say, well, that's pretty easy. I found out that I2 is 15 divided by 75, which I believe is, last time I checked, 0.2 amps. Superb. So now, if I want to know I3, I've got both these, 0.2 right here. I could just come up to this top equation, or I can just look at it, and I can say to myself, well, if I have 0.25 amps entering this junction and 0.2 is leaving, then what's left to go down in this direction? And that's just a simple subtraction problem. Or it's akin to just plugging in 0.25 equals 0.2 plus I3 right here. And it's not too difficult for you then to conclude that I3 is equal to 0.05 amps. In which direction is it? Because that's part of the question. Well, the answer is down, this way, in the direction that I chose. How do I know? It came out positive. I picked it that way, and it came out positive. Had it come out negative, then it would have been up. opposite the direction that I picked. So that's it. That's the current that this ammeter will read, since that's the flow of charge through that middle branch right there. All right, and I got it rather easily. So I didn't have to solve a system of equations with multiple unknowns. Just wasn't necessary because of the fact that I did not have an extra resistor there. Now, if I wanted to go a little further with this, at this point I could say, well, what's happening here? What's the reading on the voltmeter now? They didn't ask you that, right? That's not part of the problem at this point, but it's easy enough to figure out if I really wanted to know, because again, starting at point A and just walking my way down to point B and looking at the differences in voltage, I would say, from A to B, what happens? So I see a voltage rise of 15 as I go across the battery, and then I see a drop of IR where my current is 0.2 and my resistor is 75. So 0.2 times 75. But hold on a minute. Now wait a minute. Hold on. Check it out. That's actually 15. And then I have 15 minus 15. Wait a minute. That's actually 0. I have a 0 volt drop across from this point to this point, or from A to B. No voltage difference. In other words, the voltmeter says literally 0. That's significant. And of course that's the case, because look, there's a bare wire connected from point A all the way around to point B. Remember, idealized ammeters have no resistance inside of them, and neither does a switch, and neither does any of the wire. So as far as I'm concerned, I might as well just take a wire and just short circuit from A to B, because that is precisely what you're doing by having this loop right here. So really what you have here is just a simple circuit with a 15 volt battery, a 75 ohm resistor, and then that's it. I simply come right back around to here. This in and of itself is a path. So if there's no resistance between this point and this point along this path, then the voltage drop along from here to here has to be 0. And since this whole path is parallel with that whole path, it must have the same voltage difference across it, and that in fact is 0. So yeah, it's consistent. That's the point I want to make here. And similarly, if I did the same thing around this side, what I would find is that the voltage difference between, say, I don't know, this point X and this point X is also 0. Why? Because I go up 25 and then I lose 0.25 times 100, which last time I checked was 25. Gain 25, lose 25. So the delta V from this point to this point is 0 if I go this way. It's also 0 if I go this from here to here, because that's a bare wire with no resistance. So regardless of what the current is anywhere, in the equation V equals IR, if you're using that equation to analyze things between this point and this point along this path, well, the R is 0, so the delta V is 0 between here and here. All right, so some surprises, I think, in that. Again, all bets would have been off if I had put an additional resistor in here. That changes the problem dramatically, and now nothing that I'm saying is true. But thankfully, I don't have that, and so I'm out.